All right, here we go. Let's talk a little bit about the scientific revolution as it pertains to AP European history. So, science in Europe before 1500s is really archaic, and it's based mostly off the ideas of Aristotle and some other Greek philosophers, Ptolemy and Galen. Basically, people that are anywhere between 1500 and 2000 years before the time we are studying. And so this information is definitely outdated, and we see that in the way that people view the world. So the Aristotelian universe model indicates that the Earth is unmoving and at the center of the universe, and he argues that it's surrounded by 10 spheres, and each of these spheres contains the moon, the sun, planets, stars, and then at the edge of these spheres is heaven, and that's where God's located, according to then the Christian worldview. They place God at the outer edge of these spheres. And this is truly a common sense worldview because it explains what people see in their everyday life without scientific instruments. So you have this pioneer Aristotle who has all these ideas from 1800 years ago, but they've lived on in Europe because it fits nicely in with the Christian worldview and Christian theology. And it is these ideas that end up being shattered in the scientific revolution. And it begins around 1540 is generally the accepted beginning date. And the major causes of the scientific revolution are the rise of universities. If you will recall, after the Black Death in Europe, you have all these new universities, which gives a place for these astronomers, physicists, mathematicians to learn and to produce information. So you finally have these centers of knowledge, and because of the Black Death, you begin to have new blood in these systems, new blood in these universities, and really this quest for knowledge. And that ties hand in hand with the Renaissance, the rediscovery, if you will, of Greek and Roman works brought in from the Arab world, and this quest to learn more. Happening concurrently with all of this is navigation, and as people begin to sail, they realize they need navigational tools. They have to know where they are in the world to be able to continue where they're going. And so that really pushes science to move forward. And you get better equipment. Quite frankly, without the scientific equipment, you can't have the scientific revolution. We'd be stuck in the Greek worldview, where we're just looking around with our bare eyes. And lastly is religion. Some religions after the Reformation begin to really push this idea of science and rational thinking, either because they truly believe it or because it's another way to distance themselves from the Catholic Church and prove the Catholic Church is wrong. So these are kind of the major causes of the scientific revolution. And it brings about major changes, specifically in the fields of astronomy, physics, chemistry, and biology. And I'll just caution you to think of these fields as being intertwined. The men that we are going to look at all are, quote, experts in pretty much each of these fields. Astronomy, physics, and chemistry really have a lot of overlap in this time period. They're not as specific yet as they become later. And of course, all these men are also phenomenal mathematicians. So let's begin then with astronomy. And we'll start with Nicholas Copernicus, who kicks off the scientific revolution, if you will. And he writes this book called The Revolutions of the Heavenly Spheres, whereby he argues for a heliocentric model of the universe. That is, that the sun is the center of the universe, and the earth rotates around it. Now, this is distinctly different from the Aristotelian or Ptolemaic model, which indicated that the earth was the center of the universe. So Copernicus publishes this book. It's published just after he dies. But anyways, this book gets out there and people read it a lot. But the problem is he uses such complex math that there's not many people who can understand it or can judge its value. So although it's well read and people are hearing about this concept, there's not a lot of work to prove it, and there's not a lot of acceptance of it yet. And then we get to our friend Tycho Brahe, who's pictured here on the right. They pictured him before he lost half of his nose, so that's nice. And Brahe, he halfway accepts Copernicus's theory. He believes that other planets revolve around the sun, but he still doesn't think that the Earth is moving. So he argues that other planets revolve around the sun, but the sun and those other planets revolve around the Earth, which is a difficult concept for us to grasp because it's not terribly logical. So Brahe not only does he say that about Copernicus, but he spends a ton of his life collecting data on the position of stars. And he spends years and years doing this up in northern Denmark, where there's not a lot of light pollution at this time anyways, but he's off in his observatory just collecting tons of data. And eventually he gets this assistant, Johannes Kepler. And Kepler comes along and uses Brahe's collection of data to come up with the laws of planetary motions. Okay, and there's 3 of those, and quite frankly, I don't understand them. The one that's worth mentioning and recalling is that he proves that all planets, including the Earth, follow this elliptical orbit around the Sun, not a circular orbit, as Ptolemy and Aristotle would have argued. And they would have argued that because of the Greek thought for the perfectness of a circle. But Kepler uses all this data to indicate that it's actually an elliptical orbit. So Kepler really validates what Copernicus says. And that's because Brahe is really the bridge between the 2 of these gentlemen. And Kepler and Brahe are both funded greatly by the King of Denmark, who's interested in pursuing this knowledge of science. And of course, through all of this comes Galileo. And Galileo hears of this invention of a telescope. And the telescope had been a weapon, or had been developed to be used in war, whereby people could use it to target their artillery fire. And Galileo takes it and says, well, why don't I look at space? And this really kind of shatters, it's revolutionary. It kind of shatters people's thinking. Because what he does is he looks and sees that the moon is not this perfect, smooth surface as everyone had argued it was, but that it in fact had lots of craters and ridges and all these other features that no one had seen before. And he looks at the sun as well, and I have no idea how he does that without burning his eyes out. But he looks at that and sees that it's imperfect as well with these sunspots and solar flares. And this destroys Ptolemy's theory of a smooth, perfect moon and perfect sun, and it shatters the commonly held view. And so he's starting to undermine what had been held for years and years beforehand. Really, he's just proving Copernicus right, and Kepler. And he sees Venus that appears to change shape over time, which proves that it is in this elliptical orbit, and this proves the Copernican model of the universe. Now, frankly, I don't understand the math behind that and how that works, but that's what happens. So he publishes this in a book called The Dialogue Concerning the Two Chief World Systems, Ptolemaic and Copernican, whereby he posts 2 people having this discussion, a dialogue, about which system is better. This book is well published and well read and convinces tons of people that the heliocentric model, that is the Copernican model, is correct. The problem is the Pope reads it. And the Pope thinks that the character who is supporting the Ptolemaic worldview is supposed to be him, and he believes that Galileo is mocking him. And so you see this little power struggle takes place. The Pope is insulted, and because of this has Galileo put on house arrest, and we know that story there. But Galileo really improves the telescope, and with it he can prove Kepler and Copernicus correct. On to physics, there's 2 names you should know here. Galileo creates his law of inertia, and that is where objects in motion stay in motion, objects at rest stay at rest, unless acted upon by an outside force. And you could get a little deeper into that, but that's the basis of it. He also uses this law of inertia to prove that there is a relationship between objects that are moving and objects that are on that moving object. So he's saying a ship is moving through the water, but the containers on the ship are not feeling that movement. And that's how he justifies the fact that the Earth is moving without us feeling it moving. So that's Galileo who proves this. Again, astronomer and physicist, mathematician as well. And then there's Sir Isaac Newton, who publishes The Principles of Natural Philosophy in 1687, where he expounds on his theory of the universal law of gravitation. That's a whole entirely different concept, and I suggest finding a physics podcast if you're interested in finding out. But know that Newton develops this law of gravitation. And you'll notice it's right in the midst of all the chaos in England. In chemistry, there's 2 names worth knowing. Paracelsus, he's a physician, actually, by training. And all physicians at this time are brought up into the idea that Galen, who is another Greek thinker, has this idea that humans exist with these 4 humors, and when they are out of balance, that's when people get sick. And so the job of the physician is to put people back in balance. And that's why there was bloodletting, which was so common. Paracelsus rejects Galen's ideas. He says this isn't it. There has to be some real ideas here. There has to be something that's causing this, not this balance of humor. And so he begins treating his patients with chemicals, trying to introduce a new thing to help them get better rather than remove something to restore the balance. Now, Paracelsus is often rejected because he is also an alchemist and he injects his people with mercury and lead and other not so great things. But with him, we see the real beginnings of chemistry, and that takes off with Robert Boyle, who's about 100 years after Paracelsus. And Boyle destroys this notion that all matter shares the same structure and really starts digging deep into the way the way matter is pieced together. He also conducts experiments on volume, pressure, and density of gas, and you may recall, if you've taken chemistry before, you've heard of Boyle's law. I don't know what that is, I'm not a chemist, but it is named after him. He really is the founding father of chemistry, building off Paracelsus' ideas. Within biology, there's two names you should be aware of. Andreas Vesalius. He's a physician who emphasizes the need for dissection. Before Vesalius, people were allowed at best one dissection per year, and so this would be done then at a large gathering where all the doctoral students would gather, and the lead physician actually would not perform the dissection. A butcher or a barber would perform it while everyone else was watching on. And Vesalius simply says this isn't going to work. We really need to get into the human body to understand. And he publishes a book, De Humani Corpus Fabrica, which is about the human fabric and how the body is made, and really rewrites what anatomy is. You see, he has a short lifespan. Vesalius has run out of many of the places he goes because people are nervous about the dissection of body, and there's some accusations that he digs up people who have been buried in order to perform these autopsies. But that's Vesalius. And second is William Harvey. And he demonstrates that blood flows throughout the human body. Before Harvey, there was a sense that blood went out the liver and just kind of dissipated. But Harvey recognizes that it's cyclical, that it pumps from the heart and goes out through the arteries. And then he saw it came back from the veins. But the gap in his theory is he's not able to see how blood goes from the arteries to the veins. And that's because they hadn't developed the technology to see it yet. The microscope was not being used. It is not until 4 years after Harvey's death that someone is able to basically take a telescope and look at a body, flip it around, and view these capillaries, which is where there's that transition where blood flows from the arteries, distributes its nutrients, its oxygen, and then returns into the veins. And so that is the major advances in biology. So those are kind of the four fields. Now, there's also changes in experimentation and observation. And this can be broken down into two categories, really. You have inductive reasoning and deductive reasoning. And there's two names you should know, Sir Francis Bacon, who is inductive, and René Descartes, who is deductive. And I apologize for not having Descartes' years up there. I will track them down. Inductive reasoning, promoted by Sir Francis Bacon, ties hand in hand with what is known as empiricism. And in inductive reasoning, theories emerge after accumulation and analysis of lots of data. So you gather the small information, and from there you build out to your theory. And this, again, goes hand in hand with empiricism, which is an idea that all theories should be tested by experiments based on observations on the world around you, hands-on, and engaging with the physical world around you in order to truly understand what that world is like. And then you can come up with these theories. So it's this idea of starting very small and growing large. Opposite of that is deductive reasoning. And this goes hand in hand with another concept of rationalism. And deductive reasoning relies heavily on logic and reasoning to establish basic scientific truths or principles. Big, broad pictures. And then from there you can make assumptions about smaller items. And this is supported by this idea of rationalism, where the mind contains categories that are rational and logical and make sense, and those exist independent of any observations we make with our senses of this physical world. So Descartes argues to solve an intellectual problem, a person first needs to establish fundamental principles or truths, and then from there they can draw a specific conclusion simply using logic and reasoning. And again, Bacon is the opposite, where he wants tons of data to then build these conclusions. Descartes says you don't even need data, you can just make logical inferences. So these are the big, huge changes and names in the scientific revolution. And there are significant consequences to this. The consequences, of course, you have this development of an international community of science where all this information is traveling around. And this isn't thanks to Johannes Gutenberg and the printing press and the university system. So you have these people, a ton of whom are living concurrently and reading each other's works. They're starting to see that someone in England may be doing the same thing as someone in Poland or Italy, and they can build off these ideas. So this international scientific community starts to arise. You have the development of the scientific method because they start to, as they collaborate with each other in the scientific community, they want to ensure that they are using good, solid research, good solid observation and principles to draw their conclusions. So they demand the scientific method from each other. More broadly, you have this rise of skepticism, which is this tendency to doubt what we have been taught and are expected to believe. And this is because, again, these Greek ideas which had existed for almost 2,000 years were suddenly shattered by just looking at the sky and the moon. And so you have this major rise of skepticism throughout Europe. Again, this mostly affects the intellectuals and the upper class. Most peasants are not really exposed to these ideas yet. And you have a challenge to traditional Christian belief and an increase in secularization of European life. Now, I caution you not to take that too far, because most of these men we talked about are still extremely religious. And it's not like everyone stops going to church. But amongst the upper classes, the scientific revolution doesn't get to the lower classes. Amongst the upper classes, you begin to see the doubts, you begin to see a rise of secular ideas, and even people who become deist, which is not assigned to a particular religion, but more looking at otherworldly powers as a whole. So those are some of the major consequences of the scientific revolution. Truly a really, really important era in history, and turns us towards the modern era and really lays foundations for some other major thinkers that come along.